Welcome to the first lecture in abstract algebra. The topics that we will explore in this lecture include elementary set theory, relations and functions, the natural numbers, and the principle of mathematical induction. The foundation of all of modern mathematics is based on set theory, and so this is where we will begin. And just as in geometry, where we begin with primitive notions, undefined terms such as point, line, and plane, in set theory, we begin with the primitive notion of a set itself. A set is a collection of objects and those objects are called the elements or members of the set. So let A be a set if X is an element in the set A. We write this notation, which is read X is an element of A. If X is not in the set A, we write X is not an element in the set A. So new definition. A set is well defined if there is no ambiguity as to whether an object is or is not an element in the set. The empty set also called the null set, and this is denoted this way. Is the unique set that has no elements Now the empty set is well defined no matter what object is under consideration. It does not belong to the empty set. So let's look at another example. Let the set, which we denote z sub 2, be the set containing the numbers 0 and 1. This is called the set of integers modulo 2. And this is a well-defined set. If x is 0 or x is 1, then x is an element in the set of integers modulo 2. Otherwise, x is not an element in the set. In particular, the number 2 is not an element in the set of integers modulo 2. Now, a set is completely determined by its elements the elements in a set can be listed in any order and distinct elements can be listed more than once. For example, the set of integers modulo 2 is the set containing the distinct elements, the numbers 0 and 1. It does not matter the order in which they are listed, and it does not matter if we list a given distinct element more than once. The set of integers modulo 2 is still the set which contains two distinct elements, the numbers 0 and 1. So, new definition. Let A and B be sets. Then the set A is a subset of the set B, and this is denoted this way. If and only if every element in the set A is also an element in the set B. And if A is a subset of B, we also say that the set B is a superset of A. So let's look at some notation. This notation means that A is a subset of B. This is also read, A is contained in the set B, which is why the symbol for subset looks something like an elongated letter C. And this is also read A is included in the set B. Now, some other notation that we will use frequently include the universal quantifier, which is an upside down letter A, and this means for every, or simply every. We also have what is known as the existential quantifier, and this means there exist or there exists. If we append to the existential quantifier the prime sign, then this means there exists exactly one and if we put a bar through the symbol for the existential quantifier, then this means there does not exist. And so the definition of subset can be written in notation as follows. A is a subset of B if and only if for every element X in the set A, that element X is in the set B. And the phrase if and only if is usually abbreviated IFF. Now, if A is any arbitrary set, then the empty set is a subset of A, and the empty set satisfies the definition of subset vacuously, that is, there are no elements in the empty set that must be contained in the other set. So next we'll prove a lemma. Every set is a subset of itself. So proof, let A be a set then for every element X in the set A, that element X is in the set A, and hence A is a subset of itself. So new definition. Let A and B be sets. Then the set A is equal to the set B if and only if both A is a subset of B and B is a subset of A. So notice that the condition that two sets are equal is equivalent to the condition that both sets are contained in the other. And so to prove that two sets are equal, we must be able to demonstrate that each set is contained in the other. That is, we must show set inclusion in both directions. So let's look at some related notation. So once again, this notation means that A is a subset of B. This notation, where this symbol is the symbol for subset equality, means that either A is a subset of B or A is equal to B. If either one of these conditions is true, then A is a subset of or is equal to B. Notice that if A is equal to B, then it includes the case that A is a subset of B. And this notation, read subset not equal, or this symbol subset not equal, means that A is a subset of B and A is not equal to B. So new definition. Let A and B be sets. If A is a subset of B but is not equal to B, then the set A is called a proper subset of the set B. So as an exercise, let A, B, and C be sets. Prove that if A is a subset of or is equal to B, and B is a subset of or is equal to C, then A is a subset of or is equal to C. Okay, so new definition. Again, let A and B be sets. The Cartesian product of A and B is the set, which we denote A cross B, and this is the set of all ordered pairs where the first element in the ordered pair comes from the set on the left of the cross, and the second element in the ordered pair comes from the set on the right of the cross. So notice that if A is not equal to B, then the Cartesian product A cross B is not equal to the Cartesian product B cross A.